Hello everyone, welcome to Practical GCP. So a couple of months ago, I talked about how to use vector search with BigQuery, and I covered some of the basics on RAG, or specifically how you would generate embeddings and then store the embeddings in BigQuery and then do similarity search to retrieve the results that is most relevant to what you're looking for from BigQuery, and using some of the LLM to convert into a human readable text. And today's topic is about how to seamlessly transition from the BigQuery vector search, right, into online serving, which is offered by the service feature store as part of the Vertex AI offering. So, and thanks for some amazing work done by the Google team recently. Now to transition, let's say your experimentation, doing the batch serving, making queries to BigQuery, but into this online serving with almost a flip of a switch. So I'll show you what I'm talking about here. So this is actually very significant, and it's specifically giving how complex to transition from offline to online, and this makes it almost like completely automatic. So I want to do this first of all by describing what this looks like, right, in the setup from the raw data processing to offline to online, and why this is something important you should care. Followed by a walkthrough of the example notebook created by Elia Secchi, who is a Google engineer in the ML space. I'll cover some of the good, some of the not so good, that may need improvements, the way the kind of pricing works, and also some of the use cases in my mind that what this could be quite powerful for. Right. So why is this important? You typically have some raw data, right? And then you generate some embeddings from the raw data. The things we talked about in the last video is mostly around the first box of all offline serving. So you store the embeddings into BigQuery alongside your text, and then you can do batch retrievals. So if your data set is about how to fix my car in the BigQuery table, with embedding attached to the chunks of the text, then you can, as a user, you can do experiments to search, like for example, how to fix my car, right? That's kind of a search term you can use, and it will return the most relevant results. You can also use a scheduler to trigger the batch retrievals and then send the results to somewhere else. But these are all offline serving, that offline directly interact with BigQuery, maybe on a schedule, maybe by humans. A lot of the time, what you would want to do is to, by making the user experience very, very nice, very good, is to be able to do online serving. So that's kind of transition from doing batch retrieval of your data or your LLMs in the background, but instead putting in this particular case, using feature store to serve web or mobile traffic, which are typically requires very low response time and with very high concurrency, right? Hundreds or even thousands of requests per second on similarity search. So this framework I'm going through today is about how easy it is to make this transition from the BigQuery side into the feature store for online use cases. So let's walk through the example notebook from Elia. So this is actually a really, really good one, that with everything, I believe everything you need to know to understand how to make this transition from BigQuery into feature store, how to make this thing work. So I'll go through the most important things I think you should know from the top to bottom, not line by line, because you can try this yourself. It's actually not that complicated. But I'll cover the ones I think that are most important. So I'm using Colab Enterprise. You can use anything you like. I'm just imported the notebook into here. The benefit of using Colab Enterprise, this is actually the first time I'm using it, is you can connect to a machine. It's kind of like a a 2-core machine on like a VM that you can connect to it. So this all runs, first of all, this one within the browser, but behind the scenes, all the interaction is done with the VM in your organization. So there's nothing in public, it's all within your organization. right? So you can see here, there's a really good diagram similar to mine, but probably more the high level illustration point of view. So you have the raw data, you generate embeddings, you store the embeddings, and you have two branches. The top one is what we've been talking about in the last video, and also the offline serving and the offline kind of indexing retrieval. That's the BigQuery side. And in here, you literally have two functions, right? From each one of those classes on the top side and on the bottom side. You literally basically say, convert this thing into a feature store vector search instance, or you do the vice versa from the feature store one, then turn it into a BigQuery vector search instance. It's just one functional call, and you can switch between the offline and online storage, right? So behind the scenes, it's just basically attached to different storages. But there's something more important I want to talk to you about in this particular approach, which makes this really easy to manage, right? So I'm going to start running these things, doing a bit of reset. I haven't actually run this for a while. Make sure it still works. Okay, so now it's connected and it's done a reset. Make sure it's authenticated. Right, so here we can set a project ID and the location, importing the Vertex AI instance, and then initialize it. So here, this is slightly different to the original notebook because something on the retrieval part, creating a retrieval chain, has been deprecated. Also, I just swap out a few libraries, but nothing major. And here is setting the data set and the table in BigQuery to store this fix my car example table, right? So, right, now we're talking about document processing. This in particular is a text embedding like model that you can use to extract embeddings, basically floating point numbers from the text, right? So let's leave it aside here. Right, so here is the document. The document, so now it's basically copying that into our notebook to process it. You can see this is the document itself. The code here, you can look into the details, but basically what it does is this is a multi-page PDF document. So this is the code to basically process it page by page, and then store. It's basically kind of splitting it and then storing it by loading it into the context of using the long chain PDF loader, right? To kind of load it into the context. In this case, it will go through page by page. So just to give you an idea what it looks like. So this is actually where the document is. You've got the PDF here. I think I still have it open. Look, this is the PDF on the owner's menu of the car, right? So you've got safety, you've got child safety, you've got emergency assistance. So basically all these pages all the way to page 22, and that's where it's kind of finished. And then that's where it's kind of loading the document. This is where the 22 chunks is coming from. You can always run the metadata, as you can see, okay, so it's getting from here, the name of the document is whatever .pdf, right? So this part is where it splits the text. I used this before, but I didn't really understand it before. But now this time I actually did a pretty deep reading on how this works. So if you look at the recursive character text splitter, this is a long chain class. So what it basically does is it splits the chunk size to up to this size, right? In this case, it's 1000 in the chunk size. And it has a bit of overlap set in there. So the reason for the overlap is to kind of retain the context before and after. So you even if, let's say here is kind of a line breaks, this is the end of the sentence, exclamation mark, question mark, comma, and then you have a space and you have like a nothing left, right? So basically the separators, it will run from the left to the right, is my understanding. And then it will keep kind of splitting the chunk size until it kind of fits into exactly your 1000, and then it will kind of start storing. So if you run this, you can see it splits into 60 different chunks. So this is so this is something you can play with to see how well the search works, I guess. And then whenever it's kind of the optimum size, you kind of leave it like that, right? I haven't actually figured out any specific rules, like a pattern you can apply. You just have to follow your gut feelings to see what works better or not, and then do some experiments based on the context of your test, right? Your text. So this is a car menu, but let's say when you want to look at the SQL queries, right? To pass SQL queries, then they could be completely different to what the chunk says. You should set it to compare to this one. So now you've got your chunks of documents. If you validate it, what it looks like, that's basically it. This is what you've got. Right, now comes down to BigQuery vector store. So the vector store here is basically your connection to the BigQuery table, the dataset, the table, the location, and the project for your vector store. This actually does all of the hard work for you. So you can see this is actually initialized the rack examples dot fix my car table. And then you can add the document. So I've got something added already. So this is the schema. If you look at the preview, so I've added all of these embeddings. So I think I still have some queries. What I'm going to do is I'm going to truncate this, right? And let's re-add everything. Okay, so now I think I've truncated it, and now I'm just going to re-add everything. So this will add all of kind of the split into this document. So I'm gonna into this table, right? So you've got 35 in here, 35 document ID in here. Right, now let's do a search. Well, it's a bunch of stuff, but basically the question is, what should I do when I call the emergency roadside assistance? Then it's going to give you a bunch of documents. You can see these are documents, right? This is just how the retrieval, the similarity search for the BigQuery store works. It gives you a bunch of documents, and then that is most relevant to the question you're asking. Let's just clear this out so you can actually see this better, right? Then you can get a retriever, which will basically find the most similar document for a given query. That's what it's used for. And then all you do, this is the bit I've done a bit of change because it used to use the retriever QA, which is deprecated. I'm using the create retriever chain instead. So what this does is you can now give it a template, and you can now plug LM into it. So this is kind of giving you something that makes more sense rather than just a bunch of documents. So you can say this is your system prompt, this is your system prompt, this is your human input, this is your, it's basically glue code, and then you have your search query, right? This is the roadside assistance, same query, and then you do an invocation, and it prints the final results. The response answer payload. This bit is actually what you're looking for the final answer. So if I run this now, what it's going to do is going to make the call to the BigQuery table, does your search, basically returns a bunch of documents for you, and then finally it will give you the results. So this one basically says, look, if you're in emergency service, you need to give your car's make, model, and year, and yeah, location for the nature of the emergency, things like that. So right, so that's kind of rather than humans have to read this document, then this thing has done a pretty good job for you. Right, now it comes down to the low latency search. I prefer to call it like a kind of low response time, because this is kind of the most important thing when you search from a online use case, from a website or from a mobile app. You want something to return instantly, right? So the latency of the data does not actually matter that much, because that's kind of a, let's say you have this car menu or whatever you have, right? It kind of goes into the probably updates, let's say the feature store once a day, right? So that's kind of just the things that you that are good quality data that you want something to kind of do a similarity search on a match. Let's say in a use case that I'll probably talk about a bit later on, fraud detection, you could have things that's stored as similar to a fraud, right? Like these are things you categorize as fraud, and you store these in the, it could be someone's message or someone said something, and then when you have a message comes in the online use case, you immediately do a similarity search, and then it could tell you, oh, this is very similar. Now this could be a fraud, right? So you can do things like that. But the online thing specifically here is to basically use this particular method to vertex feature store vector store. So this will create a vector store object. But this is kind of the interesting thing, right? So this code, if you run it, so let's just run it. So because I have already created a feature store instance, so this is kind of instant. But if you haven't, right? If you haven't, so you can see I've given a online store name and then a location, right? So if you don't give it, it will create it based on a certain convention, which is the dataset is the store name plus the location that defines a unique feature store, right? So before I go any further, I want to spend a little bit of time talking about this feature store here. So when you run that code, right, this is one of the things I talked about later on probably not one of the best things to do is if your feature store in this case is called the direct example and the feature store and online shop, right? So if you haven't got it, and it will create it for you, right? In my view, this is not a good idea because you never do such thing on a production environment. You typically create this online shop, which is your feature store. There's different kind of ways you can store this. I'm just going to create it to open this thing. So you can create this is the same as the dataset name. The library specifies it's just convention based, right? And then you can do a big table based or a optimized based feature store. So there's a pros and cons for both, but for now, just the kind of most people would use the optimized one. So you don't have to specify these node count, minimum, maximum CPU utilization target. It is for more extremely high volume use cases. So if you use cases, especially when you're just starting out with LLMs with vector search, stick to this one. But my point being, this is infrastructure, right? If you just create something like this on the fly on a production system, when you're getting data from BigQuery, or if you just have a typo, it could cause quite a big problem. But anyway, this is created, and then you can see what's happening here is you created this feature store, and in this case, it's called the online shop, right? So, and then you've got your table here, right? You've got your fixed my cart. So this is actually what's done in the next step. So because I've done it before, but keep in mind you can always either get your vector store for feature store from the BigQuery instance, or you can just create it from scratch. You can do this as well, right? It's the same thing. You can do the vertex feature store vector store by supplying the same thing with project ID, location ID, dataset table. It's the same convention. You give it embedding, and then it will know what to do with it with the converting the stuff, right? So now this is the most important part. So you see back in the feature store, the online shop, I've got feature views. Those feature views. So think this way. Or each one of those feature views is a map of a BigQuery table. So this is the beauty of it, right? Every time you create a BigQuery table, right, with all of that stuff we did earlier with the embeddings, with the text you've actually stored with the embedding, you can actually sync it to the feature store as a source type. So when you create this, right, you see here, you have a various kind of ways to create the feature view, which is literally the one where you do the search, right, later on. The key thing is you can choose either from BigQuery or the feature registry. But in this case, let's keep it simple to use the BigQuery, because this is what I think the really powerful thing is, because everyone does everything in BigQuery in the Google Cloud ecosystem, especially for creating your features, right? And then if you want to use them for online serving, then it becomes very, very natural to basically link it as a BigQuery table into the feature view. So you can actually start using it. And this is achieved by this sync data function, right? This sync data function is something that you just need to call it once, and then it will sync the data. In this case is manually. If you call it sync data, it will sync the data manually from BigQuery, the table that you linked it from, into the feature store, feature view, right? That's how it works. This is really important because there's nothing for you to maintain. So if you look at how what it looks like when you call the sync, I'm not going to do the sync, and I'll explain why in a second. Is if you click into this, you can see I've done 3 already. The first one was something I've done yesterday. The first one took almost 20 minutes, and the second one took 6 minutes, and the third one took 5 minutes. Although this is very, very easy to maintain in the sense, let's say if you just set up a cron schedule rather than doing it manually, you can just let the Google scheduler to manage that for you, right? Or use the continuous one if that works, which I have not tried. But the performance of this thing is really bad, right? If you look at what my table size is, this is actually 240 kilobytes, right? So this is kind of a new version, but yesterday was very, very similar. To actually sync something like this, the first time I understand it might have to create something to initialize the feature store, but all the subsequent ones above 5 minutes. And there is a assumption that it could be, let's say if behind the scenes is using a batch data flow job, and then it could have a close to 5 minute start time. So most of these are probably overhead. But again, like, I guess if you run this daily, it probably doesn't matter. But if you want to run it hourly, it could be, yeah, it's just the overhead is quite, I don't know exactly how much time it will take to, let's say if I have gigabytes of data or even probably close to a terabyte of data, how does it manage that, right? So the performance, the speed of the transferring is not impressive. It's quite slow. But that's pretty much it on the sync part. So once you've done the sync, I think we've got an instance in here already, so right? You can then do something in the similarity search. Did you notice how quicker this was compared to the BigQuery one? It's way quicker, and because fundamentally the way it works is totally different, right? And this uses this does a very, very kind of, you can call it low latency search or something that is extremely fast. The key things later on is there are some I think let's look at some of the performance tests put in here. So now if you look at the BigQuery request, so you can see this took about 400 milliseconds to do this. But if you then look at the feature store, so now it took 20 milliseconds, which is super fast compared to what you do in BigQuery. But slow and fast is kind of irrelevant in here, but the most important thing is concurrency as well. So in online use cases, you typically have like hundreds or even thousands or even more than that request per second. So to use BigQuery to serve stuff like that is impossible. So you must use something like this, which is feature store's use case, to do those kind of use cases, right? So that's everything. So I ran through the whole thing. And it works. This is really useful. So you can actually just run through from the top to the bottom. I made a few fixes. I'll put this in a different GitHub repository you can pull. But you can see it's really, really easy to transition from the BigQuery part into the online serving part, right? So once you've done it, I think some of these things, although the Jupyter Notebooks is for you to experiment, for production use cases, you do want to in my view, to create some of these, especially the feature store instances, the sync jobs within using Terraform or using something that you can manage better rather than just using the Python libraries. Okay, the good. So just do a few summaries here. So the good part, the LangChain libraries for BigQuery and feature store vector search works really well. There's a few glitches in there, but actually you could just basically point to either one, right? So if you have a vector store instance of either BigQuery or the feature store, you can easily transition between the two, right? So from your experiment into online serving, you could easily try that, right? So what does this mean? This means when you write your code to work with BigQuery, you barely have to change your code to do online serving, and that is that is a big deal, right? Because otherwise it's going to take you ages to do this stuff. So your data is basically created an interface to allow you to have two completely different storage engines for two completely kind of distinct use cases, but with exactly the same data and the same output. So this is amazing. So, and the transition between BigQuery and feature store is just effortless. There's literally nothing you have to do about it. You just, do it as something else, and then it's done. The vector search on feature store, although I've not done load test myself, but from the notebook you can see the performance is really impressive, because that's what it's created for, right? And the bits are not so good. I think I covered some of this already. The two vertex feature store vector store probably shouldn't create the feature store itself. If you have a typo, whatever, that you could just create a new database by mistake. So again, things like this really, I think, should be done in Terraform, created as the infrastructure and maintained on a production use case. But for experimentation, you can definitely do it, right, to try it out. The sync, again, is really, really slow. I don't know why it's taking so long to do this, only 200 kilobytes. Sometimes I'm just wishing, if this is using Dataflow, I was worried, like, why Dataflow just doesn't have something that's warmed up. You can just run something that runs in 2 seconds. Why do I have to wait for 20 minutes just to get this started, and then 5 to 6 minutes each time I run it to sync 20 kilobytes of data? And keep in mind, a lot of time the syncs still took that long, even if I've changed nothing in the BigQuery table, right? So even if I've changed nothing, it still takes this long. It doesn't seem to have a way to understand something has changed or not. When you do the submission of the sync, I've actually got some RPC error because it was taking a long time. So the connection actually timed out. So I'm just thinking, I guess maybe you just shouldn't use the manual sync unless you really need it. I think ideally you just use the async, you just use the schedulers or use the continuous one. We have not tried. But if you use these ones, let's say a cron job, it does that for you automatically in the background, right? So then you don't have to worry about it. But if you call the function to sync between the BigQuery and the feature store yourself, then just watch out as it could time out, right? Because it's not asynchronous. And finally, there doesn't seem to be a way to edit the feature view. So as you can see, when you're creating a feature view within the feature store, you probably don't want to change the table it's pointing to, right? Because that's going to be a problem. But at least you should be able to change, the way to sync this stuff. Whether it's cron or continuous or manual, does it really matter? Why can't you edit this after you've created it? So here, but you don't only see the delete feature view option, which is not ideal, because if you created one is already serving online traffic, are you just going to delete it? How does that work? Right. In terms of pricing, this is kind of where it gets a bit interesting. So I started doing this yesterday, probably more than 24 hours ago. The data transfer costs can be easily controlled. So that's basically from the BigQuery part into feature store itself. Doesn't seem to cost much, and especially right now, most of you probably doing experimentation. There's not a huge amount of data in there, so it's quite easy to control. When it gets down to the standby cost, because that's something I'm trying to work out, because the documentation on pricing isn't exactly clear. So I worked out the standing cost for, you see, this is 29 hours. It costs about 7.97 pounds. So in pricing, let me see. So if you look at this page, right? So the pricing has something says about each node can have a minimum of 2 and a most of 2 replicas. So I didn't know what this means in terms of cost calculation. So the big table ones in these 2 use cases are, I think, relatively easy to calculate because you know how many nodes you put down there. But for the optimized one, which is what we typically would use, I'm not entirely sure how much it's going to cost me. So if you look at this, well, that's actually easier because this is the data processing part, transferring from BigQuery into Feature Store. And this is the online serving part. So what I've done for 24 hours is I've done literally just only a few queries. So I was trying to find out if I do nothing, would I still have to pay for it? So the answer is yes. And I think that if you times 0.3, right, based on one node, and that gives you something about $7, $8. So it's probably because of this cost, the per node hour standing charge. So obviously, if you have more requests, this will ramp up. But if it's idle, it goes into 1 but not 0. For online serving, it makes perfect sense. So it looks like that's how much you have to pay for it. The rest should be quite straightforward to calculate. So I also included this link on pricing, which you can actually look at. So I did try the price calculator, but it doesn't seem to give me exactly what I'm hoping for. So even even I'm putting down here, it doesn't seem to give me anything. This says is $36 per month. That's just not possible, because as soon as I've created the optimized serving, even I did nothing, it already cost me £7 per day. So that's not going to add up, right? So something you can try and do a bit trial and error to see how much it actually costs you. Right. So use cases, I've only included 2 at the moment because I think these are the tools I have in mind for this can be quite useful. Just as a drop-in replacement of this fix my car example. For fraud detection, think in the sense, so what's in my head is you've got, let's say, fraud that coming in that let's say if someone said something, if a certain behavior that happens, you store these things you convert them into embeddings and store in the BigQuery, right? And then you sync into Feature Store. And what you do is every time when something happens, let's say you have signals coming from transactions from people's mobile phones or the text the things that people talk about, and then immediately you call the Feature Store online search, and then if they return a similarity result, said this is like whatever probability this is a fraud, you then you can actually block the transaction. So I think that could be quite powerful. I have not tried it, but it's just something I have in mind. FinOps is another interesting one. So think of things like when this is just an idea, right? Think of when in a large organization you have hundreds of people writing queries, and a lot of people could be doing select star kind of use cases, or they are doing I don't know, like a scanning lots of data, but kind of without doing much in their queries. So in those use cases, you can actually store those queries, or maybe a certain part of the queries, that as bad practice, right? And then if you store these as bad practice, when you actually anyone kind of runs another query, you can immediately send them an email and say your query is actually not following the best practice, and this is probably the reason because of why it costs a lot. Maybe try something else. So I guess this could proactively prevent your slots gets locked out because of the inefficient queries or people using on demand to scan a lot of data accidentally. So I guess these are the use cases I have in mind that you can use them for. I'm sure there's many use cases for this, but I think the key thing in here is that you have the ease with a flip of a switch to turn something you're experimenting on from offline with BigQuery into Feature Store in online. There's still things a bit inefficient, but this can work. I tried this whole thing end to end on the notebook, and thanks for the contribution from Elia. This is amazing. So now you can actually build online applications just by flipping a switch from your BigQuery storage. This if you have to do this yourself, is actually quite a lot of effort. But now this is all built into Launcher, and you can just call it as if like a library, and then now you're suddenly in Feature Store. Be careful with your infrastructure management on production use cases, as some of these points are mentioned. But other than that, I think this is a really important and amazing addition from Google Cloud. Okay, that's the end of this. Hopefully you found it useful. We'll see you next time.
Go out!